All right, so this is going to be our lecture on state machines. So first of all, we got to talk about enums. What enums are a way to classify different objects without actually creating more classes, right? Like in this case, we would have to create a fruit class as well as an apple, orange, banana, and pear class, right? Whereas now we can just say, oh yeah, we want an enum called fruit, which contains these constants. And conventionally, these are going to be all caps. That's just how you normally do it. So for the uses of enums, they're incredibly useful in state machines. You can use it for comparisons, and typically in industry, they're used for like error types and like actually making sure that errors are handled correctly. So in this instance right here, we have an initial state where our to eat fruit is a pear, and we ask if it's a banana. So if to eat is equal to a banana, we'll print out eating a banana. Obviously, that's not true, so it's never going to print this. That's also why it's giving the little highlight there, because it knows it will never be true. So what is a state machine? Every node is going to have a precondition, a state, and an action, as well as an entry state and an exit state. You can have actions for the exit, for the entry, for the transition, or action. And I'm going to use transition or action. Or no, not transition. Sorry, precondition and action pretty interchangeably here. Because they're essentially the same thing. So then it has a state, which is basically just what's the name, some kind of description of what is contained in that state. And then an action, which is what action the state will take or what it will do. So, for instance, we can have a door closed state, right? So this is going to be our node. This is our other node right here, which is a door open. If we want to open the door, that's an action, which will cause the door to be open, and we can close the door. Pretty simple stuff right there. And then we introduce having this with enums. So we've defined our open, closed door state, as well as our state variable, which is going to track whether the door is open or closed. So we set that all up. So door state state is equal to door state open. And then we can define these two methods for opening the door and closing the door, which just sets the state to be the cause of that. So these are the actions right here. So these are the actions. And then this is going to be our initial state or init. And then what happens then is if we go through and we run this command, right, where we open the door, then we close the door, then we open the door again, the final state is going to be that the door is open. The initial state was that it was open, so this first command does nothing because it was already open, so opening again does nothing. So we can add verifications for this, where we can actually check if the door was closed and we tell it to open, it'll open the door. Otherwise, if we tell it to close the door and it was previously open, it changes it to closed. So we've only added this little bit right here, yet it will make our program, just a little bit more time efficient. This is more necessary for like higher complexity state machines where it truly matters whether or not a state gets switched. This case is pretty simple, so it doesn't really matter if you open a door and you try and open it again. You might hurt yourself, but it's not the end of the world, right? But for autonomous use, we can let's just define this green dot as our init state, so our start state. Then we can tell it, okay, hey, we want to go to this spot, we want to go to this spot, and we want to go to this spot. And then finally, let's end here. So our state machine now has a couple cases. So we know that we include 1, 2, 3, 4, 5 cases. Um, and we can use some pretty simple actions to tell us where we're at and where we need to go, because it's just a transition from one to the next. But what if we want different paths? So we can say we'll add these two cases, just for, you know, to ease of complexity, and they're all going to end at the same spot. So this is very similar to what could have been used in the center stage season, where we had to autonomously detect using vision, the current one of the three spots, right? So it's either right, center, or left. So we could say that this case 2 was right, case 1 was center, case 3 was left. It doesn't really matter. Just for this demo, it might be easier. They all ended at the same spot, at least all of my autos did. However, there was a different spot it had to go to in the in-between state, to place the pixels on the board. So we can do different paths in that case, where this dot right here would contain an if statement. But now what if something goes wrong? Let's say this state fails and we want to go back to a state. Well, we can implement that as well. And we can tell it we want to go to backwards a state. And then let's say we go again, it completes, we can move on. So that's one of those transition things where we can actually check if our state has passed or if it's failed, to ensure the robot is getting where it needs to be. So let's go through another example for a state machine. This one's going to be fairly complex, because it's a stoplight. So we'll say we have an east light, a north light, a west light, and a south light. Okay. Normal stoplight. We're not doing anything super special here. So let's expand out this state machine. Oops. So we're going to have north, which is going to transition from red to green to yellow, and south, which is going to do the same. East is going to transition from green to yellow to red, and west is going to do the same. Then we can start adding our connecting arrows, which are going to show us those transitions. We can show the transitions between the north and the south and the east and the west, to make it more defined as to trigger. And then we can add these recursive ones as well, which will bring us back. So now we can define our initial condition for this light subsystem, where we start with the north and the south on red and east and west on green. And now let's simplify it. So all we did there is we simplified it. So our north and south is going to start on green right here. Or north and south is going to start on red. East-west starts on green. Then east-west transitions to yellow, then transitions to red, which then triggers green on the north-south light, which then triggers the yellow, which then triggers the red, which then comes back, and we start the cycle again. So we have a pretty definitive stoplight right here. So let's add in some turns, some other cool things. So we can essentially make this diagram, right, where it looks complex, but it's the same thing, right? So let's start at this north-south red light. Well, that's going to trigger this if statement right here, where if the car is waiting at east or west, right? So if we're waiting to turn, and we know that we're waiting to turn, we can trigger this left arrow, or this turn arrow, one could say, which will then trigger a green light, right? Which obviously there would be some time delay, but there's not really much of a way for me to represent that here. But then that would trigger all the way through here, come back through, it would go through and trigger this if car is waiting to turn it north or south. And let's say there's not. Else, we're just going to trigger this green light, which would have been triggered anyways by this if statement through that path. But that will then trigger yellow, which will then trigger the red again, which will then trigger us back to our first if statement. So you can see there's a lot of way to define these subsystems and state machines, to make it really simple to use. But also, yeah, they can get complicated. That is, there is some truth in that statement. It gets difficult sometimes to track, But if you know what you're coding and how you're coding it, you should be fine. So for some FTC context, this was an auto that I had for Into the Deep season. Essentially, what this was using was a state machine for the arm. Right. So our arm was just a simple linear pivot with a linear actuator. So we could go up. We also had a servo at the very top for our claw. Actually, we had a couple servos, so I'll just put a weird little mark there. But it made like this action to put the arm up and in a position that could be one button press. So we can have stepwise automations where we know where current things are and we can tell it, hey, extend and then lift, or lift the arm and then extend, or pivot the arm and then extend. So there's a lot of things you can do with that as well. So moving on to a full servo example, we can go through and we'll just write this one out. But typically what I like to do is define, if this will let me do it, an enum class. Should be a space there. Servo state. And we'll just say open or closed. So then what we'll do is we'll define an initial state. So let's say claw state, which is of type servo state. So servo state, claw state is equal to, and then we'll say this one is going to be equal to servo state dot closed initially, with our semicolon, and then that's pretty much it. Then we just need to define our servo, which would be done with servo claw, and then later we would define it with hardware map dot get servo dot class, and then let's just say servo. So then what we would be able to do is we would define a void function. And this void function would say that we want to open claw, right? And what would this do? It would set claw state is equal to servo state dot open. Then we would close that off and we could define a void function for close claw. And you can guess what would be in there. It's pretty simple. But then what we would be able to do is we can add in our actual code, we will add a switch on our claw state. Sorry, these will be separated. So then what we can do is a switch statement is basically a glorified if statement, right? So then we can add a case. So case open. And then we'll add our break. And I'll explain what this does in a second. And case closed. And then break. And here we can say servo or claw.set position. I'll just say set pose 1 for this case, and then claw.set pose 0. Okay, so essentially what this switch case does is essentially this is an if right here. It would be like an if claw state is equal to open. And then we would do this claw.setPose. Essentially, that's all this does. It allows you to define each individual case and ensure that each case gets handled appropriately. This makes your code a lot more readable, and it honestly kind of makes it nicer to edit because it's not just all over the place. This break statement is necessary because technically it's a loop, and it will pass through all the way down if you don't have the break. So if I deleted this break right here, it would set the claw to closed always because of this claw.setPose0. So that's one thing to be careful of. You always need the break statement in a switch case. You could also just expand this into an if statement. That is totally doable. However, it doesn't work as well. So try and do it this way if possible. So for some considerations, don't make it too complex. Know how to switch states and when you want to switch states. Like, do you want to ensure that the robot is done with their operations and then switch the state? Or do you want to switch it before checking? It's all up to consideration. There's never a right or wrong way to do all these things, just simply easier and harder ways, and ways that you understand and ways that you don't understand. So obviously make it the way you would like to make it so you can actually understand it, because that's the most important thing about all this. And then there's a framework under my Gentrified Apps util library for a sequential state machine, which is what I used for that that driver aid stuff, where it was one button, where we could say driver aid dot set arm something, and it would automatically set it to that current state. There's a framework for that, so if you want to go look at that, it should be pretty self-explanatory, and there's a lot of documentation for that. So, thank you for watching.